Hey guys, so in this video, I'm going to cover the statistical inference. So statistical inference is basically the two things. One is about the confidence interval and the other one is about the hypothesis test. In this video, I'm going to talk about the two parameters. So when you have the population here, this is a population, you want to know the population mean mu and population proportion p. But in many cases, it's not possible to obtain the population data because it costs a lot or it takes too much time. So that's why you cannot figure it out, this population mean mu, or you cannot get the population proportion p. And by the way, this population mean mu, population proportion, we call it the parameter. So since we cannot get the population data, we get the sample instead from the population. So here's a sample. Here is a sample. And then from the sample, you can calculate the sample mean x bar and sample proportion p hat. These are, we call it the statistic. But your goal is get to know the population mean mu and population proportion p. So that's why what we want to do is you figured it out, this parameter, you estimate this parameter, that we call it the statistical inference. So you can construct the confidence interval or you can do the hypothesis test. But you realize that when you get the sample, each time you will get a different number. So you get the sample here and get to figure it out, the population mean mu, but if you do the same thing another day, you get this sample, it will get a different number. So it tells you there is a difference across the sample. And if you do it many, many times, so what I'm saying is that you get the sample today, tomorrow, so on and so forth. So you do it many, many times, that you will have the sampling distribution. And it turns out here, the sampling distribution for the sample proportion p hat, it follows a normal distribution with a mean equals the mu of the p hat. Standard deviation is a sigma of the p hat. This is the same as a population proportion p, and this is the same as square root of p times the 1 minus p over n. As long as n times the p is greater than or equal to 10, n times the 1 minus p is greater than or equal to 10, then we know that this p hat follows normal distribution. On the other hand, sample mean x bar also follows normal distribution with a mean equals the mu of the x bar, and standard deviation is a sigma of the x bar. This one is the same as a population mean, and this one is same as sigma over square root n by the central limit theorem. And central limit theorem states that as long as the sample size is large enough, so in general, n is greater or equal to 30, regardless of the population distribution, this sample mean approximately normal distribution. That is a central limit theorem. And based on this, we can construct the confidence interval or we can do the hypothesis test. But there's a difference between the sample proportion and then the sample mean. Sample proportion, you can use a normal distribution, but for the sample mean, it's too strong assumption to believe. So in that case, we don't use a t-distribution anymore. We use a t-distribution. So t-distribution is a situation when you don't know the sigma. Sigma is unknown. Also, sample size is not large. So sample size is less than 30. In that case, you should go for the t-distribution, which is a more realistic. So many cases for the sample mean, either you construct the confidence interval or do the hypothesis test, you are using the t-distribution. On the other hand, the proportion, we always use a normal distribution. So let's talk about the confidence interval first. So here, one is about the proportion p and the other one is about the population mean mu. When you get the sample proportion p hat, which is x over n, you don't stop there. You want to capture this population proportion by having this confidence interval. And then the confidence interval is nothing but p hat minus margin of error, that we call it the lower bound, and p hat plus margin of error, that's the upper bound. So basically the p hat plus minus margin of error, where this margin of error is a critical value times the standard error. But like I just said, you are using the normal distribution because of this p hat follows normal distribution as long as these conditions are satisfied. So The critical value is a z critical value, which comes from the standard normal distribution. And then the standard error is p hat times 1 minus p hat over n. So standard error is nothing but it captures the difference across the samples. Now, in general, we have 3 different confidence levels. So 90% confidence level, 95%, 99%. So based on confidence level, you need to come up with the critical value. So when confidence level is a 90%, then the alpha level is a complement, which is a 10%. Then you know that the 95%, that's the alpha level is a 5%, and then the 99%, the corresponding the alpha level is a 1%. But as you notice the notation here, z alpha over 2, then you can come up with the standard normal distribution like this, with the center equals 0 and standard deviation equals 1. So for example, you want to construct a 95% confidence interval, and you need to calculate the z alpha over 2. So z alpha over 2 is, in this case, the alpha is a 5%, then the alpha over 2 is a 2.5%, 0.025. That tells you, all right, so here, this shaded area is a 95%. And then you see that this one and that one, the left tail and the right tail, is a 2.5% each. So you have a 2 critical value. One is a negative, and the other one is a positive. So what you need to get is a positive critical value. If you're using the Excel to get this critical value, you are using the norm dot inverse, and you put the 0.975, comma, mean equals 0, comma, standard deviation equals 1. The reason that you put the 0.975 is that Excel is calculating from the left to the right. So from the negative infinite up to here, as you can see, under the distribution is a 2.5% plus 95%. So that's why the 97.5%, you can put the 0.975 or you can put the 97.5%. Once you get the critical value, you plug in here. And then the p hat, 1 minus p hat, you already know, which is just x over n. You can calculate the marginal better, then you will end up with this confidence interval. Now, for the mean, it's pretty much the same. So you get the x bar minus marginal better, that's the lower bound. X bar plus marginal better, that's the upper bound. Where this marginal better, so let's say you don't know the sigma, or the sample size is small, then you are using the t distribution, not the normal distribution. In the case, the critical value is now the t critical value, which I denote the t alpha over 2, and degrees freedom, which is nothing but the sample size minus 1, times the standard error. Because you don't know the sigma, you replace the sigma with the s, the sample standard deviation s over square root n. Likewise, in general, we have 3 different confidence levels. So let's say that same, the 95% confidence interval, then the alpha level is 5%, and then the alpha over 2 is a 2.5%. In the case, t 0.025, and then the degrees freedom. So like I said, the degrees freedom is just sample size minus 1. So for example, let's say you have the sample n equals 19. In the case, df is a 19 minus 1, which is 18. And you can draw the t distribution like this. Now the x-axis is the t distribution, t, and here the center is a 0. For the 95% confidence interval, this shaded area is same as before, the 95%, and this is the 2.5%, and here is a 2.5% as well. And let me get this positive t critical value, which is t dot inverse. So I'm talking about using the Excel and get this critical value. T dot inverse 0.975, same as a normal distribution, comma, you need to put degrees freedom. In this case, like I said, the n is given as a 19, then you just need to put the 18, which is a sample size minus 1. And after that, you go back to this marginal error equation, you plug in the number that you just figured it out by using the Excel, and then you plug in the sample standard deviation, and then the sample size, you will get the marginal better. Then x bar minus marginal better, you get the lower bound, x bar plus marginal better, you get the upper bound. That's the big picture of the confidence interval. Now, let's talk about the hypothesis test. So you do the same thing for the proportion and the mean. So proportion P and then the population mean mu. The very first step is you set up the null hypothesis and alternative hypothesis. You can say that the null hypothesis is what you used to believe. alternative hypothesis based on the sample, you have the different opinion about the null hypothesis. For example, proportion of the students who wants to have the online class is a 50%. But my experience is more than 50% of the students, they want to have the online class. So the alternative hypothesis is greater than. Well, this is a very important to figure it out, the alternative hypothesis, the sign, whether it's a greater than, less than, or equal to. When you have a greater than or less than, then we call it the one-sided test. One-sided test, you check the one side only. On the other hand, if you have the alternative hypothesis not equal to, in the case, we call it the two-sided test. Some textbook says that one-tailed, two-tailed, but doesn't matter. One-sided, two-sided, one-tailed, two-sided, doesn't matter. The term is not that important. You just need to figure it out whether it's a one-sided or two-sided by looking at the alternative hypothesis. I will tell you in a minute what makes the difference when you have the one-sided or two-sided. And then as a second step, you check the condition. So for the proportion, I said always using the normal distribution, but you need to check n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. If this condition is not satisfied, then you cannot do the hypothesis test by using the normal distribution. But this one for sure should be satisfied. And in the case, you calculate the test statistic, which is the z-test statistic. That is p hat minus p over standard error, p times 1 minus p over n. Now, there's an intuition of this test statistic. So when you draw the graph, this standard normal distribution, and here is a center 0, basically not only capture the difference between the sample proportion and the population proportion, you also consider the denominator, which is a standard error. When the standard error is small, then this is a magnified. So you either have a very large test statistic or a very small test statistic. So for example, here in this example, p equals 0.5. Just imagine that you have a p hat is a 0.9, which means that 90% of the students, they want to have the online exam. Then you have a pretty strong evidence, but that's not the end. You know that every single time you get a sample, then you will get a different p hat. That's why you have to admit that there is a standard error and you divide it by the standard error. So the whole point is when you have a very large test statistic here or the very small test statistic here, then in that case, it's very far from the 0. That tells you you do have a strong evidence to reject. But you need to know whether it's a large enough to reject or it's not large enough to reject. In the case, we need to have the cutoff point. That cutoff point, we call it the critical value, which comes from the alpha level, the significance level. So let's say the alpha level, the significance level is given as 5%. If alpha level is a 5% and the test is a one-sided like this, that tells you, all right, here, this shaded area is a 5% and that value is a critical value. And which is the same as before, that you calculate the confidence interval, which is a norm dot inverse. And you put the 0.95, mean equals 0, standard deviation 1, then you get the critical value. After that, you compare with the test statistic. So as long as your test statistic is greater than critical value in absolute, so the reason that I put the absolute is that there's a case that you get the negative test statistic and negative critical value. If your test statistic is greater than critical value in absolute, you reject the null hypothesis. Otherwise, it's smaller than the critical value in absolute, then you fail to reject the null hypothesis. You can also, so here, this one is a test statistic, this stat. You can also compare the alpha level with the p-value. So p-value is this shaded area under the distribution. You can take a look at the definition of the p-value, which is saying that the p-value represents the probability of obtaining a test statistic at least as extreme as the one observed. So that's why, which is a greater than here, the test statistic under the distribution, that's a p-value. And as you understand the meaning of the test statistic, like I said, is very far from the 0, then you have a strong evidence to reject the null hypothesis. That tells you when you have a small p-value, then you do have a strong evidence to reject the null hypothesis. What I'm saying is that p-value versus the alpha level, so your p-value is smaller than the alpha level, then you reject the null hypothesis. If the p-value is greater than the alpha level, you fail to reject. Now, let's talk about the two-sided test. So if the test is a two-sided, then you need to check the both-sided. In the case here, when the alpha level is given at 5%, what you need to do is the following. So now, same graph, the standard normal distribution, and same alpha level, 5%. But the only difference is now the two-sided test. So alpha level is a 5%. Back then, I just shaded, this one is a 5%, but now you need to divide it by 2. So alpha over 2 is a 2.5%, and this is a 2.5%, and here is a 2.5% as well. Okay, and then you have a two critical value. One is a negative and the other one is positive. Of course, they are symmetric. Once you get the one number, then the other one is just a positive sign. What about the test statistic? Well, you're gonna get the one test statistic. So let's say that your test statistic is located here. Then as you see that when you take the absolute, the test statistic is greater than critical value, so you reject. What about the p-value then? So reject the null hypothesis. The p-value is this shaded area, but that's not the end. In the case, because this is the two-sided test, you multiply by 2. Once you get that shaded area, that's going to be the p-value, and you do the same thing. So p-value, and you compare with the alpha level, then you're gonna reject the hypothesis when the p-value is smaller than the alpha level. As you can see, this graph, this specific graph, this is the shaded area. Even if you multiply by 2, still this is less than this green shaded area. So that's why you're gonna get the same decision, reject the hypothesis. Okay. Now, let's talk about the hypothesis test for the mean. So same as before, same as a proportion, you set up the null hypothesis and alternative hypothesis, mu equals to something, mu is not equal to something, that's a two-sided or less than or greater than. You figured it out whether the alternative hypothesis is less than, greater, or not equal to from the question. And then as a second step, you check the condition, but here you check whether sigma is known, and then the n is large, which is greater than 30. In the case, these two conditions are satisfied, then you can use a normal distribution. But that's not usual because sigma is in general is unknown. Why? You don't have the population data. How could you get to know that the population standard deviation without having the population data? So in many cases, it's natural to use a t-distribution. Okay. And then you calculate the test statistic. Test statistic is the following. So t-test statistic, which is x bar minus mean population mean mu over the standard error. So it's basically the pretty much same as a z-test statistic. So here, sample proportion p hat minus population proportion, you capture the difference between the sample proportion and the population parameter, which comes from the null hypothesis. And here you do the same thing, sample mean minus population mean. So you are capturing the difference between your sample mean and the population mean. Again, this population mean comes from the null hypothesis. And on top of that, you know that every single time you get the sample, you will get the different means or the different sample standard deviation that is captured by the denominator, which we call it the standard error. And after that, the following steps are the same. You either calculate the p-value and compare with the alpha level. If the p-value is smaller than the alpha level, you reject the hypothesis. And your test statistic, now is a t-test statistic, is greater than the critical value, you reject the hypothesis. So everything is the same, except now you're using the different distribution, which is t-distribution. For example, here, when you calculate the critical value with this t-distribution, it's going to be the t dot inverse. And then you put the shaded area, I'm sorry, so from the negative infinite up to here is a 0.95, but instead of you putting the mean and the standard deviation, you put the degree spread up. For the p-value, same thing. Here, you calculate this shaded area, which is a p-value, but you are using the t distribution, then you can use a t dot this. So the whole process are the same, the big pictures are the same, but the only difference between here, the mean and the proportion is a proportion most of the time, 100% time we are using the normal distribution, but for the mean, most of the time we are using the t distribution. Thank you for watching this video.